All right, so here we have another one. And I wonder what surprise this system might reserve for us. I think you see where I'm going because we did case one, case two. We did distinct eigenvalues. We did repeated eigenvalues. Now, what's left? I don't know. We'll see. So we have x prime, y prime here, just rewriting it in matrix form. And then I'm writing the coefficient matrix here. And then we have x and y. All right. So we know that to solve this homogeneous system, we want to solve the eigenvalue problem. So let me write the eigenvalue problem over here. It's going to be 6 minus lambda, minus 1 stays the same, 5 stays the same, 2 minus lambda right here. Then the vertical lines mean that we're taking the determinant of that. To take the determinant, I multiply these and these together, and I subtract the product of these two together. So what is that? And I'm also going to factor out a negative sign, so I get lambda minus 6, factor out another negative sign from that other term, and lambda minus 2 minus negative 1 times 5, and all of that has to be equal to 0. So the first thing I notice is that these negatives cancel out. That's kind of nice. Then I'm going to expand this part. I get L squared, negative 6 minus 2, that's going to be negative 8 lambda, and then I'm going to do plus 12. I think I was going a little bit too fast. Let's go a little bit slower. And then what are we going to do? Well, the negatives here cancel out, so we get positive 5, and all of that equals 0. All right, so hopefully, if I didn't make any mistakes, we're going to get lambda squared minus 8 lambda plus 17. I'll leave some space here. Plus 17 is equal to 0. So I notice that there's no two numbers, because 17 is a prime number. There's no two numbers that add up to 17, multiply to 17 and add up to negative 8, because the only two numbers that I could multiply together in the first place are 17 and 1, both positive or both negative. So I'll complete the square. So to complete the square, I'm going to look at what I have over here in this coefficient. I'm going to divide it by 2, so that's going to be negative 8 divided by 2, which is negative 4. And I'm going to square it, which is going to be positive 16. Now, you can't just willy-nilly add it to the left-hand side and not do anything to the right-hand side. So what you want to do is you want to add 16 to both sides so that you don't change this equality. This is completing the square, because now this is a perfect square. You see the difference, because we engineered it this way. Half of this squared is indeed 16. So now we can rewrite it as lambda minus 4 squared. But then don't forget you have that 17 over there. So if you subtract 17 from both sides, you get negative 17 plus 16, which is equal to negative 1. Now, if I take the square root of that, I get lambda minus 4 is equal to plus or minus the square root of negative 1. Now, the square root of negative 1 we define as I, so plus or minus I. So I can say that lambda is equal to 4 plus or minus I. Now, once you get to this point, really nothing changes. Yes, you have a complex eigenvalues, but still, you can just plug him back into this equation. So why don't we do that? We're going to say 4 lambda 1 equal to 4 plus I. Well, now we're going to have this system, 6 minus 4 plus I, don't forget the parenthesis, minus 1, 5, and 2 minus 4 plus I. All of that. And we're going to have here, we can say x and y, and that's equal to 0, 0. This is the eigenvalue problem. If you don't remember where it comes from, I invite you to look at earlier playlists. Sorry, not earlier playlists, earlier videos in this playlist, and I explain where that happens. I think it was exercise 3, so the first one in the playlist. So once I have this, let's simplify it a little bit. So 6, if I distribute that negative, I get 6 minus 4, that is 2, and then minus I. Then here I get negative 1, I can rewrite that. I can rewrite the 5, and I get 2 minus 4, that's negative 2, plus I. I close this right here. I get an X and a Y. Close this, and that's going to be equal to 0, 0. Okay, well, now you might ask, well, how are you going to prove that the top row is dependent on the bottom row? I'll show you once. We won't do it more than once, but I think it's very cool to look at. So here we have 2 minus I times X minus Y equals 0, and 5X minus 2 plus I plus minus 2 times I, Y equals 0. All right, so let's say I want negative I here. Well, sorry, negative Y here. I'd have to multiply by the negative of the coefficient. I have to divide by the negative of the coefficient of Y. So if I divide everything here by negative 2 plus I get 5 divided by negative 2 plus I plus, and actually I have to divide by the negative of that. So the negative of that, which is positive I and positive 2 negative I. And here I get negative Y, and that's equal to 0. So, okay, that does not look like the top. But can we make it look like the top? Can we make it look like this? I don't know. Let's see. So, if we multiply this, oops, and let me move it here. If we multiply this fraction by 1, we're not going to change the fraction, right? So what if that 1 is a very fancy one, which happens to have the conjugate of the bottom one? The conjugate is the same real part, but the opposite of the imaginary part. Well, then we would have at the bottom 2 plus 1 times 2 minus 1 is the difference of squares. So that's going to be 2 squared minus I squared. The top, however, is going to be 2 plus I times 5 minus Y is equal to 0. The bottom is going to be 2 squared, which is 4, minus I squared. Now, what is I squared? All right, well, what is I? I is equal to the square root of negative 1. I squared is going to be negative 1. So we can write negative 1 here instead of I squared. Negative 1. And that becomes 2 plus I times 5 divided by 4 plus 1, which is 5, which cancels out, minus Y equals 0. And for some reason, I forgot the X. That is, I'm sorry if that confused you. So notice how this now is 2 plus I times X minus Y equals 0. And that looks exactly like this. So even if they don't look the same, imaginary numbers are, special. They make things look different when they're not. So all this to say that to find our eigenvector, we can use just the top one. So we can say that 2 minus I times x is equal to y. So let's see. If I let x be equal to 1, then y is going to be equal to 2 minus I. And I can say that my k1 is equal to the vector 1 and 2 minus I. Don't get worried about the I. That's just an I. That's just a complex number, but it's still a number. It still has a right to be included in our awesome math. And now, the cool thing is that the other vector, k2, is going to be the conjugate of this one if it comes from the conjugate of the lambda, the eigenvalue. So it's going to have the same 1, but here we're going to have 2 plus I. And then you should know this theorem. Well, okay, you could write the solution in a couple ways. One way to write the solution 1, you just say, hey, it's still my k times e to the lambda t. So this is the one case where you would write 1, 2 minus I times e to the, what was our lambda, 4 plus I times t. And our second one would be k2 e to the lambda 2 times t, which is 1, 2 plus I, the conjugate, e to the 4 minus I, the conjugate, times t. And then you would add them together and you leave them like this. But then, if you wanted to, you could rewrite this as using Euler's identity, which is e to the I pi equals the cosine of pi plus the sine of pi. If you were to do that, you could rewrite it using Euler's identity. And if you were to do some manipulation, you could use theorem 10.2.3 from the book. And this theorem looks like this. It says, take the first vector k1 and rewrite k1 into an imaginary part of k1. Sorry, I'll put the real part first. A real part of k1 and an imaginary part of k1. So that's going to be, what is the real part? Well, it's just 1 and 2. And the imaginary part is 0 and I. See, if you add them up, you get back this vector over here. But we actually wanted the first vector, sorry. So if you add them up, you get this vector over here. Now, if you call this B1 and call this B2, you can write that one solution is equal to B1 times the cosine of what? Times the cosine of, see, we gotta think, times the cosine of beta, which is the imaginary part of this, times t, plus b2 times the sine of beta t, so not plus, minus b2 times the sine of beta t. All of that multiplied by e to the alpha t, where alpha is the real part of the eigenvalue, and then x2 is going to be b2 times the cosine of beta t plus b1 times the sine of beta t e to the alpha t. Okay, so let's see. x1 is going to be b1, which we said is 1 and 2. The vector 1, 2 multiplied by the cosine of beta t. Beta is the coefficient of the I in the eigenvalue, which is, let's see, our eigenvalue is 4, lambda 1, 4 plus I. So the coefficient of the I is 1. So we write 1 times t minus, then we have our b2, which is 0I. And this is where things get a little bit weird. You don't write I here. We write 1 because we're intending that that's the coefficient of the I. So here this becomes 0, 1, and this is negative because we should write it like this. And this negatives come from the formula. And then from that, we write sine of beta, which is, what is beta? It's the coefficient of I, which is 1. So we're not going to write it. And then from that, I'm going to multiply by e to the alpha. Alpha is the real part of the eigenvalue, which was 4. So 4 times t. And then we can write x2 by following this same process. But now we have b2, which is 0, negative 1, times the cosine of t, plus b1, which is 1, 2, times the sine of t. Close that, e to the 4t. The general solution is going to be c1 times x1 plus c2 times x2, which is going to be c1 times 1, 2 cosine of t minus 0, negative 1 sine of t e to the 4t plus c2 times 0, negative 1 times the cosine of t plus 1, 2 times the sine of t, close that, e to the 4t. And this is the answer because we don't have any initial condition to determine the C1 and C2 as well. This is our result. And I hope, so you can rewrite this and make it a little bit prettier if you want to. So I hope this was helpful, and I will see you next time.